that. All right, so get this to line up. Let's see if it will be able to see it. All right, guys, so if we are looking at our atoms, yes, we want to look at how are these things going to connect. So we talked about with dehydration synthesis, they go together, they'll kind of snap together, but how does every atom, how do we know how many openings it has? How do we know which pieces it can snap together with? So the way that we do this is on the periodic table, we know how many electrons are there. And we have this idea that the first layer can hold 2, every layer after that can hold 8. So if I were to diagram out a hydrogen ion, okay, a hydrogen atom, I would have my center, which is my nucleus. I'm going to just put the H in the center to signify I'm looking at a hydrogen. Now, for my hydrogen, I have 1 electron because it had the atomic number of 1. So if I take a look here, I have my first valence. My first valence can hold 2 electrons. That's how much can fit on the very first layer around the core of my atom. My hydrogen had an atomic number of 1, so I can fill in 1 electron spot. So that means my hydrogen atom has 1 electron and it has 1 open space that it can react with. Are we good with this so far? So how would, if I have a hydrogen to hydrogen, how would that interact? So let's say I draw, I'm going to use 2 different colors here. So if I have my hydrogen here, and I have 1 open space and 1 electron in red, and then I'm going to do my green hydrogen that I want to have bonded, and it's going to have 1 open space and 1 electron. So when we do this, what we end up seeing, and this is when we get covalent bonding, is the electron from atom number 1 will fit into the open space on atom number 2. Atom number 2's electron is going to fit into the space from atom number 1. Does this make sense? Can we see how those fit together? Are we good? All right, so this is our hydrogen. This is what you would put in your hydrogen box on the pear deck.
You want us to draw that?
Huh? Yes.
Okay.
Now, if you want to simplify, we can do it with our Lewis dot structures, which just take the circles out. If I were to do that, it would look like my hydrogen with 1 dot and my hydrogen with the other. That would be as our Lewis dot structure version, where we have kind of brought it in. And it's a little bit simpler. This is actually how we type it. If you had to like type out a paper and you're talking about bonding, this is one of the reasons why we usually draw the electrons right above, below, and to the left and right, is I can use just a regular word processing and make the dots in the right spot. Are we good with this idea of hydrogen with hydrogen? Somewhat. All right, so now we're going to try a slightly more complex atom. So we had our hydrogens, they had the atomic number of 1, and then we have an oxygen. The oxygen's atomic number is 8. Okay, this is something you would find out by looking at the periodic table. I'm not asking you to memorize this. So now if I were to draw my oxygen, okay, so again, I'm only looking for this on the Paradeck. I'm not looking for you to draw the whole molecule, just the simplified version, but I want you to see where that came from. So our oxygen, if I draw my nucleus of my oxygen, right, we got our little nucleus there with oxygen. I'm going to have my first layer. My first layer has 2 spots for electrons, so we're able to fit in 2 spots for those electrons. My next layer can hold 8 electrons. So I'm going to draw these as empty right now. So if I have my first 2, I need to get to how many electrons? How many electrons did oxygen have? 8. 2 of them I used to fill in my first layer. So now I'm at number 3, number 4, number 5, number 6, number 7, and number 8. So I now have 2 spots that oxygen is able to interact with other things. Yes. You can write it in your journal, but I would like you to do at least the simplified version on the Paradeck.
So just when you write the simplified version, just write that. Okay.
All right. So does this make sense if we look at this oxygen atom? Now, guys, just like the stack of cases at like an Aldi's or at Costco, are we able to interact with that center ring? No, just like you're not going to like pull something out of the bottom case of a stack of cases, we're not interacting with the center rings. It's only this outside ring. So we have 2 spots that can interact. Now, if I was to draw this as our simplified version, I have my oxygen, and I would only draw the outer ring. I wouldn't draw all of the inner rings because it's not necessary. Because the only thing reacting is the outer ring. Are we good so far? Where did I lose you? For which one? Guys, green table, can I have you focus, please? All right, so now if I want that oxygen to interact with a hydrogen, my hydrogen, remember, has only 1 spot it can interact. So is my hydrogen going to be able to interact with both of these? No. Can it interact with one of them? Yeah. So if I put in a hydrogen here, is my hydrogen now happy? The red circle, is it all filled? Is there any open spots? No, right? My open spot got filled in with one of the oxygen electrons. Hydrogen's happy. Is oxygen happy? No, oxygen wants to react again. So what it's going to do is, instead of just reacting with 1 hydrogen, like my 2 hydrogens did, my oxygen's going to get a second hydrogen to interact with. Now, what did I just make? It's our water. Guys, the reason why we don't just see OH is if all we have is OH, it has an open spot. It's trying to find something to react with because it's got an empty spot to try and do something with, right? We're not going to see OHHH, right? Because it doesn't have another spot to react. Does this make sense? Are we good? This is kind of the core when we look at chemistry and we're trying to figure out, will these things interact? If we go back to the periodic table and we can see how many spots they have to interact with, this is how we kind of figure out and try and puzzle piece how these molecules can be built. Are we good with this idea? All right, so if I were to draw this in a simpler, like Lewis dot type structure. I would draw it like so. Now, both of these types of bonds, the HH and the OH, they are both showing covalent bonding. They're called covalent, co meaning to share. The valence is the name we have for the circle around the atom. Both of these are sharing the circle. The circles are overlapping. We call it covalent bonding. Guys, my best analogy for this is like the absolute best friends. Over here, we have the pair of best friends. Right here, we have the trio of best friends. Everybody know a group or a pair like this where if you invite one, you have to invite them all. You will not see one without the rest. They travel everywhere kind of together. Everything they do together, right? Guys, this hydrogen doesn't care if there's another oxygen around. It likes this oxygen and that's it. They stay stuck together. Are we good with this idea? All right, so this is different than ionic bonding. When we talk about ionic bonding, rather than BFFs, okay, so this is like our BFF, this is our covalent. And this is like our BFF bond. Our other type of bond is called ionic. Our ionic bonds, these are like our French fry friends. How many of you have known someone who only shows up if you happen to have a thing of French fries in front of you? Right? If you don't have any French fries, they're not hanging out. But if you've got French fries, suddenly they seem to come from nowhere and they're like, hey, we haven't talked in a while. You don't mind sharing, right? Everybody familiar with this behavior? Ionic bonding is closer to French fry friends. They are going to interact because there's a charge, not because they want to stay stuck together. Just like if I have the thing of French fries, if I slide that thing of French fries down the table, those people who are only there for the French fries, they also slowly move down the table. They don't continue your conversation. They're like, oh, I can have a conversation with this person over here. Same idea. Now, with our ionic bonds, we're going to look at a slightly bigger atom. So we're going to look at sodium and chloride. So sodium has an atomic number of 11. So we're going to first start drawing that one. So if I draw my nucleus for my sodium. Now, guys, the reason why sodium is Na and not S is the language in which sodium was first discovered and put on the periodic table. Their word for sodium started with Na. Does this make sense? So we will see that sometimes on the periodic table, the letters don't match the name. That is because it does match in the language of the person who documented it all and got it on the periodic table into their language, because we don't all have the same names for every substance. If we have a different word for it, whoever discovered it gets to use their own language to name it. Does that make sense? All right, so for sodium, we have to get to 11. So our first layer was 2. Then we're going to have our next layer. Our next layer has 8. Now 2 plus 8 gives us how many? 10. Do we need more layers? Yeah, we are still not all the way to 11. So our second layer is going to be all the way filled in. And then we need a third layer. Now, once we have added in this third layer, can we interact with our second layer? No, it's covered up. It's no longer something we can interact with. So I've got 10 electrons and here is my number 11. So if we look, how many open spots does sodium have? 7 spots that are open. Guys, this is like if you have like the big cardboard case of stuff at the store and there's only the one thing sitting in it. People will just go ahead and take that one thing out to be able to use the box, right? Sodium really wants to have 8. Do you think it's going to be an easy thing to find somebody to share 7 electrons with them? No, so sodium's going to go the other direction. Sodium's going to be like, you know what? I am okay if this one electron leaves. It's not going to hold on to it too hard. It's going to be like, hey, you know, I'm okay. If you want to leave, go ahead and get out of here. All right, so let's look at our chlorine. Our chlorine has our atomic number of 17. So if I was drawing that, I have my chlorine in the center. I'm going to have my 2 on my first layer. I then have my next 8 on my second layer, bringing my total to 10. And then on my next layer, I am going to have to fill in 7 more to get to my 17. So guys, how many openings does chlorine have? Just 1. That's all chlorine has. Chlorine is willing to take an electron. But chlorine, is it a little molecule? No, it's going to have 17 protons there in the center that are going to be trying to yank on that extra electron. Chlorine isn't trying to share. Chlorine is trying to be like the French fry friend and be like, yeah, you don't really want that electron, do you? I'm going to go ahead and get those electrons out of your way, and I can go ahead and deal with that extra electron. So if we were to do this simplified, remember, I don't have to, if I'm doing it simplified, I don't have to draw all my center layers. Sodium can have just my 1. And my chlorine would have 7 dots, doing my like Lewis dot structure here. And what chlorine is going to do is chlorine's going to be like, yeah, you don't really want that electron. I'm going to go ahead and take it. Does this make sense? When it does that, what we end up with is chlorine has 7 of its own electrons and 1 of sodium's electrons. The sodium now has a positive charge because remember, it used to be even, right? It had 11 pluses, 11 minuses. It got rid of one of the minuses. So now we have 11 pluses and only 10 minuses. My chlorine has that extra electron. It has an extra minus. The reason they stick together is the plus and the minus. Are we good with this idea? Did I lose anybody? Do we see the difference between this one and this one? All right, so let's look at our sodium and our oxygen. Our sodium, remember, is our Na with just 1. And now let's pull an oxygen down. I use blue for oxygen. And then I have my oxygen hanging out here. With the 2 openings. So guys, do you think oxygen is going to want to share with sodium? Is sodium trying to find lots of people to share with? He's trying to get rid of that electron. He's like, you can take it. I really don't want this around. Go, get out of here. That electron is just going to go over to the oxygen. Now, oxygen is super greedy. It loves electrons. It is going to steal up as many electrons as it can. And when it steals up those electrons, it ends up leaving 2 sodiums without an electron. And my oxygen over here ends up with not just 1 negative, but 2 negatives. Are we good with this idea? Guys, how many of you have heard of antioxidants? Yeah, right? We've got them in stuff we put on our skin. There's stuff that we eat that has them. An antioxidant literally is there to try and combat oxygen. Oxygen, just sitting here in the air, is actively yanking electrons out of you. That's what it does. It likes doing it. We have things that rust because oxygen is yanking the electrons out of the metal. The oxygen that you breathe in, the reason why we have to have oxygen to live is our oxygen. We actually use this characteristic of oxygen at the end of our electron transport chain during respiration. We end up with all these extra electrons. We don't want them. We breathe in oxygen. Oxygen goes in and basically binds to all of them and then attaches to a hydrogen pair of them and turns into water. All of the air you breathe in becomes water in your body as it basically absorbs the waste electrons that get released during metabolism. Does this make sense? That's why we have to breathe in oxygen, is it's to be able to soak up those extra electrons, because oxygen is a greedy atom. Are we good? All right. So our exit question, guys, is, and I will put it back on that screen here in a second, and I will post the video of this explanation. Huh? All I'm having you do is just like the Lewis dot on the slides. So guys, for our exit ticket was simply, what was the main difference between the 2 types of bonds? What was the main difference between covalent versus ionic? And I will go ahead and put that screen where I was working it out with you here. Back up. So remember, covalent are like our BFFs. Ionic are the French fry friends. They're there just for the charge. They are not actually staying connected. If another charge comes by that has an extra plus, that oxygen's going to go hang out with whatever else had the plus charge. If there's an extra minus, those sodiums are going to go hang out wherever there's an extra minus. Yes. So our covalent is when we want the 2 atoms are sharing. This usually occurs if neither one is missing a whole lot of electrons. So we see covalent when in our outer shell we have like 1 or 2 missing, and so that we can just share a little bit and then everybody's happy. Yeah. For which one?
The covalent.
The ones I did with the square around them. So this was my simpler, the 2 hydrogens, simpler oxygen. For my ionics, it was just these Lewis dot. Here would be the simpler version versus the black and yellows. Yes. What was that? An ionic bond is after an atom has taken an electron, it's minus. Ionic bond is like magnets sticking together. They'll stick to something else, right? Like it's, they're still their own thing. They're just sticky because they got a charge. Covalent. Ionic bonds. there. Because the electron kicked out of one of the atoms and the other atom. Now, guys, one other quick thing. Please remember, I'm not going to have you have to like do a full diagram. This is so that this is supposed to be reviewed, but if you never had covered it, I wanted to make sure we could visualize how these molecules, how these atoms snap together, so that when we're talking about like glucose is snapping together and other, like why it works the way it works.